Hello class, welcome to this video on the 5.1, 5.3 test. This is the multiple choice has 5.1, 5.3. The free response has a little bit of 5.4. But let's go over both portions in this video. So the first question, when a fair die is rolled, the probability of any side landing face up is 1 out of 6. Which of the following is the best interpretation of the probability of rolling a 5? So we're interpreting the probability. So the first one, when you roll a die 6 times, exactly 1 time a 5 will land face up. Remember that probability is not guaranteed. So even though you would expect that one time there would be a 5, if you roll the die 6 times, that doesn't mean it's guaranteed. So it's not A, okay? It's not an interpretation. If you roll a die 600 times, exactly 100 times a 5 will land face up. Again, that's how many times you would expect it to happen. That doesn't necessarily mean that that's the interpretation probability. As you roll the die over many and over many times, the number of times a 5 would land face up out of the total number of rolls would get closer and closer to 1/6. That is what we're looking for. That is the interpretation. It's getting closer and closer over many and many trials. That's the law of large numbers. The answer is C. All right, number 2. 3 of the following statements contain myths about randomness. Which of the following statements is true? A fair 6-sided die will be rolled 60 times. The die will end up face up on each side exactly 10 times. Now, this is similar to the probability argument that if you roll it 60 times, then 60 divided by 6 is 10. You would expect it to be exactly 10 times on each thing. That's not necessarily true, right? That's not how probability works. It's a long run kind of thing. The probability of having to stop at a certain stoplight is 0.40. If a driver that passes this light every day to stop at it 5 days in a row, the next day the driver passes the light, the driver likely will not have to stop at it. No, this is using the law of averages, so this is incorrect. Remember, the law of averages is incorrect, meaning, and it states that if something happens a lot, then it's unlikely to happen the next time. And that's not how randomness works, okay? Randomness is random, so it could happen 5, 6, 7 times in a row. It's completely random. So remember, the results are not guaranteed in the short run. When using a random number generator on a calculator to select digits from 0 to 9, it is just as likely to get the sequence 01234 as it is to get 99999. And that is true. Remember, the thing about randomness is that it's random. And so you're just as likely to get these numbers in that order than you are to get all 9s. That's just the way it works when you do a random number generator. They have the same odds of happening, the same probability. All right, so the answer is C. All right, so number 3, two fair die, dice. 2 fair dice are rolled, and the sum of the numbers that are face up are added. What is the probability of rolling a sum of 10? All right, so we have 2 dice. Remember, there's 36 possibilities for the 2 dice, right? So let's do that over here. So you can get 1 all the way to 6. And you get 1 all the way to 6. Okay, so you can get 2 1s. You can get a 2 and a 1. You can get a 3 and a 1, so on and so forth. You get a 2 and a 1, so on and so forth, all the way up to a 1 and a 6. You get a 2 and a 2, and so on and so forth until you get both 6s. This could be a 6 and a 1, 6 and a 2, so on here. 2 and a 6, ... Okay, so there's 36 possibilities. So we want to see which ones have a sum of 10. So when we add the 2 numbers, they add up to 10. So that would be, for example, 4 plus 6, right? So let me write that one down. 4 comma 6, that adds up to 10. 5 comma 5, that adds up to 10 as well. 6 comma 4, that adds up to 10. So these are the possibilities for adding to 10, right? And so the probability here is 3 out of 36, which is 1/12. All right, so here the answer is, so it looks like they have 3 out of 36. So we can actually just use that as the answer since they didn't reduce the fraction. All right, so the answer is D. All right, number 4, if for the upcoming school fair, each ride requires from 0 to 3 tickets to ride, the probability distribution of the number of tickets for a randomly selected ride at the fair is shown below. What is the probability that at least one ticket is required for the ride? So let's say the number of tickets is X. So what's the probability that X is greater than or equal to 1? So at least one ticket means 1 or 2 or 3 or 4, right? So instead of adding these up, what we can do is we can do the probability of 0 and then just subtract that from 1. So 1 minus the probability that is for 0 tickets. And so it's 1 minus 0.1, which is 0.9. And again, if you added these up, you would also get 0.9. All right? So the answer is D. All right, number 5, for the upcoming school fair, each ride requires from 0 to 3 tickets to ride. Okay, so same thing. What's the probability that more than one ticket is required to ride? So this is the probability that X is greater than 1. Okay, so that means you 2 or 3. So that means the probability that X is equal to 2 plus the probability that X is equal to 3. So it's going to be 0.3 plus 0.4, which is equal to 0.7. So the answer is C. All right, number 6, the teachers at a local high school were surveyed. 2 of the variables recorded were for the 150 teachers were housing status and length of service. Housing status was recorded as owning or renting your residence, while length of service was classified as a new teacher, less than 5 years of service, or as an experienced teacher with at least 5 years. All right, so based on the responses, what is the probability that a randomly selected teacher from this school is a teacher who has less than 5 years of experience? So a randomly selected teacher is a teacher who has less than 5 years. Okay, so so the probability of less than 5 years of service, right, is equal to, well, how many teachers have less than 5 years experience? So new teachers, that's a total of 30. So 30 out of the total of 150, right? And that's what they're looking for. So number 6 is D. Number 7, so the same idea, but this time it says, what is the probability that a randomly selected teacher is a school who has less than 5 years of experience and who owns their own home? All right, so I'm going to say new teacher, or yeah, so I'm going to say probability of new and owns their own home. All right, so there are 5 new teachers that own their own home. So that's got to be 5 out of 150. All right, so that's number 7 is C. Number 8. So number 8, it says, based on the responses, what is the probability that a randomly selected teacher from the school is a teacher who has less than 5 years experience or owns their own home? All right, so remember the probability, let's call this A and let's call this B. The probability, or yeah, let's actually use the same variables. So it's yeah, let's just call this A. So I'll call this A, I'll call this B. So remember, the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. That's the general addition rule for any 2 events, A and B. So what's the probability of selecting a teacher with 5 years of teaching experience or less than that? Well, it's 30 out of 150, right? Probability of B. What's the probability of selecting a teacher that owns their own home? 80 out of 150. Minus, what's the probability that we get a teacher that with less than 5 years experience and who owns their own home? 5 out of 150. So combine those results together, so you get 110 minus 5, or 105 out of 150. 105 out of 150. So the answer is C. All right, so let's look at number 9. All right, so number 9, at a local high school, 30% of the students are on a school sports team. 25% of the students take at least one AP class, and 10% of the students are on a sports team and take one AP class. All right, so we'll say on a school sports team, so we'll call that event S. AP class, we'll just call that A for AP class. And then 10% of students are on both. All right, so the probability, and then they said if a student is randomly selected from the school, what's the probability that the student is on a sports team or takes at least one AP class? So the probability of S union A, right? Remember, we wrote the formula here. It's the probability of S plus the probability of A minus the probability of S and A. Okay, so what's the probability of S? Well, there's 30% of students that are on a sports team. What's the probability of A? Well, 25%, at least take one AP class. Minus, what's the probability of S and A? Well, they said that 10% of students are on a sports team and take at least one AP class. So there you go. So 0.55 minus that is 0.45. So it's 45%. So the answer for 9 is C. All right, number 10. In Mr. Rogers' Algebra 2 class, 45% of the students received an A on the first test, 50% of students received an A on the second test, and 35% scored an A on both tests. So we got 35 on both, 45% on A, and 50% on B. All right, so give the Venn diagram for this situation. Find the probability that a randomly selected student from Mr. Rogers' class receives an A on only one of the tests. All right, so let's just do the Venn diagram. So we got test 1, test 2, right? So when we do this, they said there's 35% on both tests. So 35% of students scored an A, right? So there's that. Now, 45% of students scored an A on the first test. So this has got to be 10% because 10 plus 35. And then there's 50% of students that received an A on the second test. So this has got to be 0.15 because 0.15 plus 35 is 50%. All right, and then so then we got, so far, if you add up these totals, we have 45% plus 15% is 60%. So that means 40% of students did not earn an A on either of those tests. All right, so it says, what's the probability that a randomly selected student receives an A on only one of the tests? So one of the tests means either this one or this one, right? So it's going to be 0.10 plus 0.15, which is 0.25. All right, so which one is it? 0.10, 0.35, 0.15, 0.40, and 0.25. So the answer for this one is, let me see, is it B. All right, so number 11, shown below is the Venn diagram for the events A, student from the first class got an A, and B, student for the second class got an A. Find the probability of A prime intersect B. All right, so this is the students that are not in A, but they are in B. So this is A, and then this is B. All right, so they're in the second class, but they're not in the first class. Well, that's just that one, 0.15, right? So that's there is A. Number 12, shown below is this Venn diagram. It's the same idea. This is A, this is B. Find A prime given B. So we got a conditional probability. All right, remember, so to calculate conditionals, I'll write down the formula. The P of A given B is the probability of A and B divided by the probability of B. So what's the probability of A and B? Well, that's this one right here, 0.35. That's what they have in common. Oh, actually, wait, we want to do it for this formula. So let's do it for this one. Okay, so the probability of A prime given B. So A prime given B is the probability of A prime and B divided by the probability of B. All right, so what's the probability that they're not in class A, but they're in class B? Well, that's 0.15. All right. So we got 0.15. What's the probability that they're in class B? Well, that's going to be 0.35 plus 0.15, right? So B is all of that. All right, so 0.15 out of 0.50. And let's see what that is. So 0.15 out of 0.50. So that's 0.3. So the answer is C. All right, number 13, shown below. So this is, again, using the same Venn diagram, A and B. All right, it says, in this example, P of A given B is 0.7. What is probability of A given B prime? Are the events independent? Let's actually calculate to see if that's true, okay? A given B. Is that true? Well, A and B divided by the probability of B. Now, what's the probability of A and B? 0.35. What's the probability of B? 35 plus 0.15 or 0.50. Okay, 0.35 divided by 0.5 is 0.7. Okay, so they're right. I just want to double check that. So it's 0.7. So now what is probability of A given B prime? So it's the probability of A and B prime divided by the probability of B prime. All right, so how many students are in A but not in B? 0.10. How many students are not in B? Meaning that they have to be in A. But not in B, right? So not B. So not B is 0.10 and 0.40, right? Because 0.40 is not in B technically. So we're going to shade, so it's basically 0.10 plus 0.40. So it's 0.10 divided by 0.50, which is 0.2. Okay, so it's either A or B. Now compare these. Are these the same? The answer is no. Since they're not the same, they cannot be independent, okay? That means they're not independent, okay? So the answer is A. All right, number 14. Suppose a card is selected from a standard deck. What is the probability of selecting a king or a red card? Probability of king or red card. All right, well, use a general addition rule. Probability of king plus probability of red minus probability of king and red. So in a deck, there are 52 cards total, and there are 4 kings. So there's 4 out of 52 for the probability of king. Now, there are 2 colors. There's there's red cards and black cards. So that means half of the cards are red, half of the cards are black. So 26 out of 52 are red. And then minus, we want how many king cards are also red? Well, there are 2 king cards that are red, okay? Because there's 2 red king cards, there's 2 black king cards for a total of 4. All right, so we got 30 minus 2, so it's 28 out of 52. And then we'll convert that to a decimal here, 0.538-ish. So the answer is C. All right, number 15. Suppose a card is selected from a standard deck. What is the probability of selecting a jack and red card? All right, so the probability of jack and red. So how many jack cards are red? Well, there's 4 jack cards, 2 of which are red. So it's 2 out of 52, which is 1 out of 26. And then let's do 2 out of 52, 0.038. Okay, so the answer is C as well there. All right, and we got a couple more. So 16, a survey of 100 people was sent out asking if they were cat people or dog people. 30 people said they were not either cat people or dog people. So they were not neither cat people nor dog people. 10 people said they were both cat people and dog people. 35 people said they were dog people. Draw a Venn diagram. Okay, so we got cat, dog. So it says 30 people were neither. So 30 on the outside. 10 people said they were both. 35 people said they were dog people. So that means this has to be 25 because 25 plus 10. All right, and we surveyed 100 people in total, right? So that means, okay, so let's add these up. 30 plus 25 plus 10, that's 55% to 65. So 100 minus 65 is 35. Okay, so then this has to be 35 so they can add up to 100 people. All right. And then what is the probability that a person likes cats? Okay, well, it's both of these put together is cats, right? So it's 45 out of 100 or 0.45. So the answer is B. All right, number 17, D and F are two events where P of D is 0.4, P of F is 0.15, and P of D or F is 0.32. What is the probability of D and F? Okay. All right, so it says D or F, so let's use that formula. The probability of D or F is equal to the probability of D plus the probability of F minus the probability of D and F. All right, so let me write this down over here. Now they give you D or F is 0.32. The probability of D is 0.4. The probability of F is 0.15. So you got to solve for X. I'm just going to call that X. All right, so there's an algebra equation. All right, so combine these. That's 0.55. Subtract this on both sides. So you get 0.23 negative equals negative X. And so X is equal to positive 0.3. Both of these are positive because if you switch the signs, okay? All right, so X has to be 0.23. So the answer is B. All right, so it takes care of the multiple choice. So let's look at the free response. All right, so an airline claims there is a 0.25 probability of a randomly selected business traveler will check baggage. An agent at the check-in counter records whether each business traveler checks baggage. Explain what the probability 0.25 means in this setting. All right, so you're just going to interpret what probability of 0.25 means in this setting. Okay, so remember, law of large numbers. If you do this many, many times, a very large sample, okay? So if you select a very large random sample of, in this case, you're talking about business travelers. Yeah, so business travelers. Roughly 25%, or you could say about 25%, right? About 0.25 of them, or 0.25% of them will check baggage. Okay, so there's the law of large numbers at work there. Does this probably say that if 100 business travelers are selected at random, exactly 25 of them will check baggage? Explain. If 100 business, so remember, in this case, 0.25, that's a fourth, right? So if you have 100 business traveler, a fourth of 100 is 25. So we would expect that 25 will check baggage. But does that mean that exactly 25 will check baggage? No. Remember that probability is not guaranteed in the short run. It's a pattern over many, many repetitions, okay? So no probability is about what happens over many, many repetitions of a random process. So it is not guaranteed to get 25, to get exactly 25. All right. So something like that. If you say something like that, it's not guaranteed in the short run. It only happens in the long run over many, many repetitions. All right, part C, the agent observes 6 out of 12 business travelers who check baggage. She would like to know if this outcome provides convincing evidence that greater than 25% of the business travelers check baggage. To help answer this question, we want to perform a simulation to estimate the probability that 6 or more out of 12 business travelers will check baggage. Describe how to use a random number generator to perform one repetition. So basically they want us to describe the simulation. I mean, we just want to do one repetition. All right, so in this case, since there's 25% chance that they check baggage, on a random number generator, we're gonna say one. The number 1 is that they check baggage, and then we'll say 2 through 4, 2, 3, and 4. That's 75%. 2, 3, and 4 will mean they won't check baggage. And then we're gonna generate how many random integers? We're gonna generate 12 numbers, okay? Because there's 12 business travelers, and we want to see, okay, we're gonna generate 12 numbers from 1 to 4. And then we're going to count the number of ones that we have, because that'll tell us how many check baggage, okay? And that's what we want to do. We want to perform a simulation to estimate the probability that 6 or more will check baggage. So we need to count the number of people that check baggage. All right, so let 1 equals check baggage. And 2 through 4 equals don't check baggage. All right, and so what we want to do is use a random number generator to generate 12 random integers like whole numbers, from 1 to 4, to simulate business travelers and whether or not they check baggage. Okay, and then we're going to count the number of ones. All right, so in other words, number of those who checked baggage. Okay, so something like that. So if you said, okay, 1 is baggage, 2 to 4 not baggage, generate 12 random numbers from 1 to 4, and then you say count the number 1, something like that, then you're fine. You don't have to say 1 is baggage. You could say the number 2 is baggage, and then 1, 3, and 4 are not. I mean, you can do something weird like that, but it's just easier. It's more obvious and easy to just do that, right? 1 is check baggage, 2 to 4 not. Now, to determine if these data provide convincing evidence that more than 25% of the business travelers check baggage, 100 simulated samples of 12 business travelers were selected, assuming that 25% check baggage. A dot plot shows the number of business travelers in each simulated sample. So part D, use the results of the simulation to estimate the probability that 6 or more of the 12 randomly selected business travelers check baggage. So 6 or more. So here you go. 1, 2, 3, 4, 5, 6, 7. We got 7 of them, right? So the probability is 7 out of 100, which is 0.07. So there's a 7% chance. Okay, so we got, there it is. That's all we want. It's 0.07. That's what they want. Based on the actual result of 6 business travelers that check baggage and your answer to part D, is there convincing evidence that more than 25% of business travelers check baggage? Well, remember that this probability, right, which is that we got 0.07, is actually less than or equal to our cutoff of 5%. Remember that when we did this lesson, 5% was the cutoff. So if it's less than 5%, that means not less than, I'm sorry, greater than 5%, not less than. So if it's, remember that the results states that if it's less than 5%, then that means we have enough evidence, we have convincing evidence to reject, the claim or whatever. But here we have greater than 5%. And so we do not have enough evidence. We don't have a convincing evidence that more than 25% check baggage, okay? So 7% is, in other words, 7% is somewhat likely, okay? So no, since 7% is somewhat likely. 5% and less is not very likely. But once you hit past that 5%, it becomes somewhat likely to happen. So since 7% is somewhat likely, that 6 plus out of 12 business travelers, I'm just going to say 6 or more, out of 12 business travelers will check baggage. There is not convincing evidence that more than 25% of business travelers will check baggage. All right. And that takes care of free response question number 1. All right, free response question number 2. Suppose you spin a spinner with 4 equal sections, red, blue, green, and yellow, 2 times. List all of the possible outcomes for spinning 2 times. So all the possible outcomes. All right, so we have red, blue, green, yellow, and we're doing this 2 times. So that means we're going to have 2 colors. All right, so you can list out all the things of the sample space by making a nice organized table if you want. So we can say red, blue, green, yellow, red, blue, green, yellow. And so we have R, 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 B, red, blue, red, green, red, yellow, blue, red, blue, 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 green, blue, yellow, green, and then red, green, and then blue, green, and then green, green, and yellow, and so on and so forth. There's a total of 16 options, 4 times 4. All right. So list all the possible outcomes. That's the sample space. Define event A as spinning blue at least once. Find the probability of A. All right, so probability of A. We want to spin blue at least once. So that means 1 or 2 times. Okay, so let's write down the events for A. What are the events that allow us to do blue at least once? Well, we can have red, blue. We can have blue, red. We can have blue, blue, of course. We can have green, blue. We can have yellow, blue. We can have blue, green. And we can have blue, yellow. 2, 4, 6 looks like 7 options. So we have 7 out of 16, which is 0.43. Approximately 0.438. But you could leave the answer as 7 out of 16, but I'll just put it as a decimal if you round it to 3 decimal places. All right, so number 3, a local restaurant is handing out coupons to customers as part of a marketing promotion. The coupons are all of equal size, well mixed, and have the name of a free item written on them. Here is the probability model for the items the customers can win. Explain why this is a valid probability model. All right, remember, for this to be a valid probability model, the probabilities have to be between 0 and 1, which is true for all of these. And so I'm going to start with that. Each probability is between, and it could be equal to 0 and 1, is between 0 and 1 inclusive. So that's good. That's check. The next thing is the sum of the probabilities has to be equal to 1. Okay? So we got to add these up to see if that's the case. 25 plus 25 is 50. That's 50, so this is 1. The probabilities add to 1. All right, good. So therefore, yes, it is valid. Okay, find the probability that a customer does not win an entree. So this is E for entree, the probability of not entree. All right, so the probability of E prime is equal to 1 minus the probability of E. That's the complement rule. So 1 minus 0.05 is 0.95. All right, that's it for number 3. Number 4, last question, or I think there's 4 and 5. Okay, last 2 questions. Among 120 middle school students, 70 like ice cream, 40 like strawberry ice cream, and 30 like both. Make a Venn diagram to display the sample space of this chance process using events C for chocolate and S for strawberry ice cream. Don't forget the rectangle as well, that's part of it. All right, so it says 30 like both, so it's 30. 40 like strawberry, so this has got to be 10 for a total of 40. 40 like chocolate, so a total of, or 70 like chocolate, so it has to be 40 for a total of 70. And there was 120 middle school students, so far if we add these numbers, we get 40 plus 30 plus 10. Let me go back to it. 70, 80. And so this has to be 120 minus 80 is 40. So we got 40 right here. All right. So it says find the probability that a randomly selected middle school student likes chocolate or strawberry ice cream. So, all right. So I said probability. Oops. We got chocolate, union, strawberry. All right, so again, if we use the rule, if you use the Venn diagram, a C or S is just going to be anything in C, anything in S, and including both, right? So you can say 40 plus 30 plus 10. You can do that, or you can use the general addition rule. So I'm going to use the general addition rule. So the probability of C plus the probability of S minus the probability of C intersect S. So the probability of C is 70. Okay, so we got 70 over 120. And then we got the probability of S. S is 40 people like strawberries, right? Over 120. Minus, and then 30 people like both. All right, and either way, you're going to get the same answer, whether you use the rule or whether you use the Venn diagram. So we got 110 minus 30, so it's going to be 90. So again, or 110 minus 30 is 80, rather. Okay, you can do that, or you can just add these 3 numbers and you get the same answer. All right, over 120, and then make sure to reduce that. So you can reduce it, or you can convert it to a decimal. So let's see, let's just do it as a decimal. So this is going to be 2/3 or 0.667. Find the probability that a randomly selected middle school student likes chocolate ice cream but not strawberry ice cream. All right, so the probability that they like chocolate but not strawberry. If they like chocolate but not strawberry, that's going to be this 40 group, right? So it's 40 that like chocolate but not strawberry. So it's going to be 40 over 120, which is 1/3 or 0.333. All right. Okay, so the next one is what's the probability that a randomly selected middle school student likes chocolate ice cream given that they like strawberry ice cream? All right, so there's a couple ways to this one. Again, you can use the Venn diagram, or you can use the rule for conditional probability. So what's the probability that the selected middle school likes chocolate ice cream? So likes chocolate given that they like strawberry. So the rule is probability of both divided by the probability of the given. All right, and then the probability of both is, well, it's 30 out of 120, right? There's 30 that like both. And then strawberry was 40 out of 120. And notice that these cancel out and leaves you with 30 out of 40, or 3/4, which is 0.75. Another way of looking at it is, okay, given strawberry. So given the strawberry, which is this right here, given that, what is the probability that, so out of those people, which in that red circle, how many of those people like chocolate? Well, 30, right? So 30 out of 30 plus 10, so 30 out of 40. All right, so that's another way of looking at it. But you can look at it, and you can look at it as either way. But there's a way to look at it if you like to think of it that way. All right, so let me get rid of these. Okay, so number 5, we finished up with the last one. A census of students 8 at a very large high school was taken, and each was asked their grade level. Okay, so this is, have we seen, I feel like we've seen data like this before, but we have large cafeteria, small cafeteria, student center, and then we have their year. So freshman, sophomore, junior, senior. Suppose we choose a student at random from these 2,540 students. Find the probability of selecting a junior. Okay, so probability of junior. Okay, so there's 635 juniors, right? Out of total 2,540 students. All right, so let's do that on the calculator. 635 out of 2,540. So you get 0.25, so 1/4 or 0.25. All right, the probability of a senior and large cafeteria. All right. So how many people are seniors and they're in the large cafeteria during one of the 3 lunch periods? So senior, there's 350. Okay, so 350 of them out of total of 2,540. Okay, again, do that as decimal or we'll reduce it. Yeah, 0.138. Again, 3 decimals is fine. Find sophomore or probability of sophomore, union, or student center. Okay, so again, you can add the 2 probabilities. So probability of sophomore plus the probability of student center minus the probability of both, right? So probability of sophomore plus the probability of student center minus the probability of both. All right, so sophomores, there are 650 sophomores out of 2,540 plus how many students are in the student center? 595 out of 2,540 minus the probability of both sophomore and student center, which is 125 out of 2,540. Okay, so let's do the math there. 650 plus 595 minus 125. So that's 1120 out of 2,540. Yeah, 0.441 if we round it to 3 decimals. All right, and then part D, find the probability of freshmen given small cafeteria. So probability of freshmen given small. All right, and then remember it's the probability of both. divided by the probability of the given. All right, so what's the probability that they're both freshmen and they're in the small cafeteria? That's 435. So we got 435 out of 2540, and then the probability that they're in that you have a student in the small cafeteria is 860 out of 2540. Okay, so these cancel. You get 435 out of 860, and we'll do that here. So you get 0.51506 if you round it to 3 decimals. All right, guys, that's going to do it for the video. Hope you found this useful, and as usual, I'll see you in the next one.